So that's pretty cool, hey? Look at that. The Fibonacci sequence has given us phi just by comparing successive terms. That's pretty amazing, right? Okay. Now, here's what's going to happen though. I'm about to disappoint you. Because I said that's pretty amazing, yeah? Actually, it's not so amazing, okay? Watch what's going to happen. I'm going to look at another sequence now. I'm going to start in a similar way. So what I'd encourage you to do is to copy out, select these two columns here. So I'm going to select, you can use your cursor or you can just go shift and then move your cursor keys to surround them. I'm going to copy that and I'm just going to go, bless you, into this space over here and I'm going to paste it, okay? My columns will need to be adjusted a little bit so that they're a good width to show the numbers. Okay, so I'm going to call this next sequence Mr. Wu's sequence. Okay, and the reason why will become clear in a second, right? Now you remember, with the Fibonacci sequence, what we did was, we started with these two numbers. They're really important. So I'm going to highlight them just so you can see them. So let's make them both red, shall we? Okay, hope you can see that. So those two numbers, they're kind of like the seeds for the rest of the sequence. Once you know those numbers, the rest of the sequence just kind of unfurls. It just follows the rules. Right? Well, what I'm going to do is, I'm going to take a different pair of numbers as my seed. Right? And the pair of numbers I'm going to take is a pair of numbers that I really like, which is 19 and 9 because that's my birthday. Right? So I've started with two completely different numbers. But otherwise, I follow the same rule to generate these, the rest of the sequence. All right. So have you got the same numbers that I've got? Can you see that? Now, I've got 19 and 9. Now, in fact, what you can do, if you want to blow your mind even a little more or disappoint yourself a little more, instead of 19 and 9, you know what? Just pick your own numbers. Maybe you want to put your own birthday in there. Okay, so I've got 19 and 9. Maybe you're going to have like the 5th of August, so that you'll be 5 and 8. Okay? Whatever two numbers you put in there, you'll have a different sequence. So now here's what we're going to do. We're going to generate this third column again, that ratio column. Okay? So what I'm going to do is I'm just going to take that top one there. That was where I put my first ratio calculation in. And I'm going to paste it in the corresponding spot in my sequence. Okay? I'll need this column to be a bit wider as well. Okay? And so you can paste it into the corresponding spot on your sequence. Right? Now I've got 0.473684. That's because that's the ratio between 9 and 19. 9's smaller. That's why the ratio is less than 1. So far, so good. Your ratio might be bigger depending on what your birthday is. Okay. Now I'm going to take that and I'm just going to paste it. I'm going to see what happens as my sequence progresses. Now your ratios ought to be slightly different to mine. But if you go far enough, something interesting will happen. It's interesting or disappointing depending on your point of view. I'm going to make mine even a little bit wider than that. And I'm going to copy this guy across. Okay, what's happened? Well, on my sequence, my ratios start off all wacky and weird, but then, wait a second, I'm still approaching phi. And so should you be. Whatever numbers you put in the top. Right? Look, if you've got two computers between the two people on your desk, look over at your friends. They'll have a different birthday, I hope. Well, does anyone here have the same birthday? Yeah, okay, we all have different birthdays. Different ratios, but we all converge. We all converge on phi. Right? So in fact, it doesn't look like the Fibonacci sequence is so special after all. If you build it with the same rule, you always end up at phi, no matter where you start. But I said I was going to amaze you with the Fibonacci sequence. I said I was going to disappoint you by showing actually it's not so unique after all. Now I'm going to blow your little mind by showing you actually there is one of these sequences that is more special than any of the rest. Okay? So this time let's go again. Take your Fibonacci sequence, go down to the bottom, copy it, right? And go over to the right hand side, paste it in. You should have an exact copy of the Fibonacci sequence again. But this time, when we look at those seed numbers, this time we're all going to put the same one in. This sequence is not called the Fibonacci sequence. It's called the Lucas sequence, named after a mathematician named Lucas, unsurprisingly. Okay. Now he made the most minuscule of changes, right? I should just quickly ask, is anyone's birthday the 2nd of January? Anyone? No? Okay, well, we're just going to imagine that Lucas's birthday is the 2nd of January. Okay? So if he were to make his birthday sequence, it would be 2 and 1. And then you hit enter. Okay. Now, before I go any further, I'm just going to, and you should copy that in as well, I'm just going to note that 2 and 1, right, even though they're the seed numbers, if I change their order to make it 1 and 2, I get a different sequence. In fact, have a look at this. What sequence is this? This is the Fibonacci sequence again. Why is this the Fibonacci sequence? We started a different pair of numbers, didn't we? Why did we get the same sequence back? Look back at your Fibonacci sequence if you have to. Why did I get it? Yeah, Eric.
Because it just starts at a further place.
Very good. 1 and 2, they are still parts of the Fibonacci sequence. It's just the next terms. I just don't start at the beginning. I've started further in. So for example, if my seed numbers were 5 and 8, right? 5 and 8, let's go back over here. Then you will expect I get further along in the Fibonacci sequence, but it's still the Fibonacci sequence. So I come back, what I really want is not 1 and 2, but 2 and 1. Okay, now if you look at this, and I do my ratio comparison again, okay, let me make this a bit wider. If I do my ratio comparison again, like we saw before, I'm going to approach phi. No big deal, they all approach phi, right? So that's no surprise. But this time I'm going to do something a little bit different. Okay, a little bit different. I'm going to delete out this column because it's actually not that important to me. I'm going to go to this, this cell here, and you're going to need that phi number again. So if you can't see it nearby, like I can't because mine is too large, my spreadsheet is too large, I want you to copy it so that it's somewhere nearby so that you can access it. Okay. I want you to go down to the 0, 1, 2, Lucas number 2. Okay, I'm corresponding to that end column. Okay, so this is Lucas number 2. Okay, Lucas number 2. Start a calculation. Okay, equals. Okay. Now what we're going to do is I'm going to take phi and I'm going to raise it to a power, right? Phi to the power of whatever Lucas number I'm up to, the 2nd or the 3rd or the 4th or the 5th, right? Now you might notice, looking at your keyboard, again, you don't have a power button. So we're going to use this symbol, which is above the 6. Okay? It's called a hat, right? Because it kind of looks like a hat, okay? So we're going to go hat, which means to the power of, and I want you to go and click on the corresponding, like which Lucas number am I up to, right? Which is 2. So please note, it's not what is the Lucas number, it's which Lucas number, okay? So I don't mean 3, I mean 2. And I hit enter. Alright, now hold on a second. I've got too many decimal points here, so I need to take a few off. I'm going to do a few more. Okay, so I've got a number, which seems a bit random. That would be unsurprising because phi is a messy number, so phi to some power will also be a messy number. But I'm going to try and continue this pattern, right? Now, before you continue it, I want you to go back to this cell, right? It should say a very similar thing to mine. And I want you to change something. See where it says, I've got J1, okay? Yours might be somewhere else, depending on where phi is in your spreadsheet, okay? You might have it on A2. Who has it on A2? Hands up, anyone? Or B1, sorry, it's a B1. That's better, yeah, B1, okay. So if yours says B1 there, that's fine. I want you to put a $sign between the B and the 1. A $sign, okay? I'll explain what the $sign does in a minute. I'm just going to hit enter for now. Your number shouldn't have changed, okay? But now I can copy that formula. Can you see 2.618? Have you guys got that? Yeah. I'm going to copy that and I'm going to paste it below. And then I'm going to paste it below again. And again. And again. And I'm going to keep going all the way down to the end of my list. What do you notice? What have I got? This series of numbers I've just developed, which is phi cubed, phi to the power of 4, phi to the power of 5, phi to the 6, phi to the 7. Oh no, I missed. That's phi to the 6. That's phi to the 7, phi to the 8, and so on. What are they giving me? These are giving me the Lucas numbers. Can you see that? All I need to do is approximate. Let me make it obvious for you, okay? If you go to this, this column that we just created, okay? And let's reduce the number of decimal places that we've got. So it's the icon next to increase number of decimal places. So let's decrease. Whoops, mine's not working, so I'm just going to do them one at a time. Right? If you decrease it so that you've got no more decimal places, you're just rounding off, okay? You can see it always rounds off to the corresponding Lucas number. Exactly. All the way down. Look at this. Look at this guy, right? In fact, the further we go along, the more exact you get. 5 to the power of whatever will give you, look at that. Look at this one. This is equal to the Lucas number to the 5th decimal place, right? That's astonishing. The Fibonacci sequence is not magical because it approaches 5. It's just like every other series because it approaches 5. But the Lucas sequence, that's incredible. Look at that correspondence. And in fact, if you go down, let's just copy this a bit further. These numbers are too big, so you start to run out of decimal places. But it continues. The pattern continues, and if anything, the pattern gets even closer.